Afternoon, ladies and gentlemen. In our last lectures, we discussed differential equations, and I was able to present the general formula for a first order, first degree linear differential equation. You recall that I asked you to hold on with certain questions because we wouldn't have much time. Now, today we are going to discuss the application of differential equations. And the first thing that I'll talk about is about time path in market models, and then I'll go to other applications of differential equations. Now, this is a course overview, and specifically these are the things that I'll be looking at. The reference lists, please consult them. Now, notice that we can use differential equations more or less to know the time path in market models. Or even when you talk about the growth of anything, we should be able to know how, the growth of any macroeconomic indicator is as time approaches infinity, right? Now, I'll look at it using a very simple example of demand and supply, okay? To be more specific, let's assume that we have this to be the demand, there's the supply of a commodity. At equilibrium, it is not difficult to prove that the price is what you have over here. That is, if you equate demand to supply and then find P, you are going to get something over here. The major problem we'll be investigating is that this price, there can be destabilization in this price, okay? That is, demand can increase, supply can increase, or vice versa. So what would you, and when any of these things, happen, the dynamics, price changes, okay? It may increase or decrease based on whether there is a shortage or whether there is an excess. But then what we would like to know is that in the long run, would price come back to equilibrium when there is any destabilization in the price? We can do these things or investigate the nature of the price, destabilization as time approaches infinity with the help of what? Differential equations. Now, one thing we would like to assume here is that the rate of price change with respect to time at any moment, it's always directly proportional to the excess demand. And that is quite implicit, that is quite clear. So when you have price changes here, you have a proportionality constant here, which is equal to the difference between demand and supply. So whether there is, demand is more than supply, what it means is that, prices will go up. When the reverse, occurs, so prices will come down, and they all depend on time. And as I said, the excess demand over here, or shortage or whatever, is being adjusted with the help of this constant. And as I said, our interest is that if there is stabilization, and then in the long term, as T approaches infinity, will this our price come back to our equilibrium level? This is what we are going to do now. Let's be more practical here. In our equation that I set off, right, what I've done is that if we put in the demand and supply equation that I mentioned earlier, and then reorganize them, we get something like this, okay? But further, if we make the substitution that V is equal to what we have standing here, and then Z is equal to what is standing over here, we are going to have this. What does this remind you? This reminds us of a first order, first degree linear differential equation where there's the derivative. This is the term that determines the homogeneity. This is the price. So, as I said, with this equation, if you go back to our last lecture, we can straight away write down the solution for this equation using the formula that we have over here. Okay? So, when you use the formula, we write our general solution, and when we simplify, we can simplify further, and then we get something of this nature from this equation. Let's make some assumptions. Initially, like when the time was 0, the price P of T was equal to P of 0. The idea why we're doing that is to find the constant A here. So when we put these values in there, we have the constant A to be what we have over here. So we slot the constant in again here, and then we have this equation. All right. So this is how price, okay, of this commodity moves with time, right? This is how price moves with time. Now, there is one thing I would like you to go back and check. Notice that we have V to be equal to that, and then Z to be equal to that. So when we slot it in this equation, okay, when we slot in this equation, we have this, And if you go back to our initial equilibrium definition of equilibrium, then we have what we have standing over here. So in place of this one, we put the P prime, put the equilibrium price, and we have the P price over here. Now my question remains. Now, if this is the initial equilibrium price, all right? Now, if there is shortage or if there is excess, the price will move, or the change in the price here will depend on this additive. So the question is that, is it possible that in the long run, okay, we will have this additive being equal to 0 such that the price P of T here will return to the equilibrium price P of P with a bar here, right? The question is, under what condition would we have this additive turning into 0 so that the dynamics of price will go back to equilibrium? This is what we talk about dynamic stability. Now, if you look at these additives, right? So under what conditions are we going to have this to be equal to 0? We know that all these P of 0, you know, P, M here, they are all positive, okay? So when T tends to infinity, it means that the price over here, or P of T here, will tend to P prime if and only if H minus B is equal to 0. Because if H minus B here is equal to 0, we have a negative here, we have 1, so it turns out to be 1 over e raised to the power this amount. So when this one is positive, and then we have this multiplied by infinity, so it means 1 divided by e raised to the power infinity becomes a very small number that it turns into 0 as what T turns into infinity. So the only condition under which we will have this one turning into 0 as T approaches infinity is when H minus B, right, is greater than what? 0. Under that condition, then we say there is dynamic stability. Simply, it means that if there is any destabilization in the price, in the long term, that is when T approaches infinity, the price will return to the equilibrium. Otherwise, it will not turn into equilibrium. Now, let me take a very practical example. So here I've defined my demand, defined my supply. I've given some initial conditions to enable us find the constants, and therefore, you know, our equation, you know, is what we have over here. When I slot in the actual values and then sort of look at it or simplify this, I have this equation, which is equivalent to our first order first differential equation, where V is equal to that and then Z equals to that. It means I can write my general solution straight away. What I'm left with is how to more or less simplify this integration. This integration gives me that. I slot it in here, expand it, and then when I, you know, reorganize them, I get this nice equation here to be our solution. Right. Now, we have some boundary conditions. Notice that in this solution, we have two constants here, A and then alpha. So once we have two constants, we need two boundary conditions to be able to solve and find the actual value of A and alpha. So these are the constants. So when we slot them into the equation and simplify, right, we get these values to be over here. What do we have? We have our, let me see what our A is equal to. We've still know our A is equal to 3, sorry. So when we slot the two boundary conditions, our A comes 3, and then our alpha here comes to this value. So we go and plug the values back, and this becomes our differential, the solution to our differential equation. So this is how price will move, you know, with time. And the next point is that, is there going to be dynamic stability? That is, if T tends to infinity, will this additive turn to 0? So you see that we have this one. If T tends to infinity, will this additive turn to 0? If this additive turns to 0, then it means our price will turn to our equilibrium price 3 over here. Now, we see that as T tends to 0, we will have this one here, which, you know, when we put infinity here, it means we are going to get, you know, our 3, and therefore it means there is dynamic stability in our equation. There's an example here which I've made it a little more complex, but you can just take your time and go through. So here, in the same properties or the same equation, but then I've given my demand and supply in this form. In this form here. So to solve this equation, we have the change in price being proportional to the excess demand. So we plot in these values, and then we simplify, and in the long run, we have an equation of this nature, which is also the same equation over here, which is, there's a first order, first degree linear difference equation, the same as what we have over here. So we can write the solution using the formula, and using this formula, we write our solution as we have over here, and further, when we simplify them, we have an equation of this nature. Then we go further and investigate our dynamic stability, and once we have this one, if this one is greater than 0, then it means we will have dynamic stability. So the only condition which can ensure dynamic stability is this condition. So this one is greater than 0 if and only if this one is greater than, is B is what, greater than, F. And therefore, we would have, if B is greater than minus F, actually, B is greater than minus F over here, and that can ensure dynamic stability. I have some examples for you here, and I would like you to take your time and study that. Now, apart from that, as I told you, let's have some selected applications. One thing I need to mention is that differential equations can be applied in so many fields, okay? It is left to you to look at the question and try to see how best you can solve it. If you look at this question over here, we've been given that the rate of change, all right, of a certain lakeside community is what we have over here. So the change in the lakeside community is given this equation, and is the population, the change of the population with respect to time, is what we have been given here. We're also given this equation, that the rate of change of the population with respect to the environment is equal to that. Now notice that by chains rule, we can have this equation, right? That is by chains rule, and which means that the PDT would give us this equation. When we put them in and simplify, and this becomes a differential equation, which we can simply, separate the variables. So when we separate the variables and then we solve them, right, we have this equation. There is a boundary point. We use the boundary point to find the constant, which we obtain to be 60, and therefore this becomes the rate of the population equation in terms of time. If you want to know the population at any point in time, all what we need to do is that we just, put the time in, and we're able to estimate the population at any time t. There is also another equation here, right? Here we have the price of a certain house, which at the time t equals 0, the price is equal to this. The rate of change of the price is what we have over here, okay? And we are supposed to estimate or find the cost of the house in 9 months. This is what we have been given, how the price changes with time. And if we reorganize this equation, we can put it in this form. And if we compare it to our first order, first degree differential equation, our V is equal to that, and our Z is equal to that. So this looks like, or it is a first order, first degree linear differential equation. It means that we can straight away write the solution. So this is our general, equation, and therefore we write the general solution for that equation. This integration is quite easy. We can do it over here. Integration over here, we have to use our prowess in integration, and here the best way is to use integration by parts. So further, you've seen that we have used integration by parts to resolve that integration, and when we plot them back, we get the situation. We have boundary points to find the value of the constant. So from here we get the value of the constant to be A. So we plot them back, and then this becomes the price of the, the property, which depends on time. Notice that we're asked to estimate the price, the cost when t is equal to 9. So we slot the 9 into the time, the t over here, and then we are able to estimate the cost at time t equals 9. Now, I have very nice activities for here. Please take your time and then go through, and if you do have any problem, let's meet at the chat room. Thank you.